That's a Shelley Physics Introduction to Rotational Mechanics. This is a unit that's going to review pretty much everything we've done so far in the class: kinematics, forces, energy and momentum, all that kind of stuff. Newton's laws is applied to those systems. But before we're looking at it in a translational motion kind of view. In this unit, we're going to be looking at rotational motion and how all those concepts apply. So you get a great review of all those other concepts. We're not really learning anything brand new. This is just a different way to look at things. Instead of translating side to side or up and down, we're rotating clockwise and counterclockwise. So that's going to be the big difference here. But everything else is a small difference. We're still going to look at how force affects motion, how mass and inertia would affect the acceleration of an object as a force is applied to it. But in this case, we're looking at how objects are rotated instead of translated. So for all intents and purposes, mainly the center of mass stays put, and the body itself is what we're looking at. We're not thinking about the object moving in space, called translating, but instead how it's rotating in space. And towards the end of the unit, we'll put everything together. So we'll have scenarios where things are translating and rotating. So here are just a couple of situations. First, we're going to look at mainly an object as a circle, just a simple object that can rotate. And if we rotate it, let's say from one position to another, it rotates through a certain angle instead of being translated through a certain x direction or y direction of space. We'll look at spinning objects, sort of like this, kind of like a top, but also some irregular objects. I have a cello here. What if we rotate something like a cello? We'll even get some irregular kind of objects. We'll also look at how pulley systems, where the pulley itself has an impact on the acceleration of the system because it is a rotating object itself. We'll look at how different shapes roll down hills differently. You might be surprised after what we studied so far, but at the bottom of a hill, if the whole object is rolling, it may not roll the same as another different object where the two objects look much different. All right, so just to get us started here, we need to have some terminology, some words that we use that are similar to our past experiences with motion, but we need to throw in some new pieces here. So we're going to borrow some information from geometry from a little while back. You might recall, let's say from here to here, if we go along the edge, this is called an arc length. Just bringing out some old terminology, an arc length. Now the arc length I've defined here is exactly one radius of length. So if we take a radius, a radial line here, and measure it, and we lay it like a string over the edge of this circle, what I'm saying here is this arc length that I've defined here is about equal to r, the radius of the circle, and we have another radius here. Now if I define this kind of wedge of the circle in this way, then the angle right here is equal to 1 radian. As you can see here, I've got 3 radians of angle that almost makes up half of that circle. So of course that little piece here would be about 0.14 radians. And altogether that half the circle is 3.1415926, so on. Pi radians is the angle around one circle, is equal to 180 degrees. The arc length formula you might have learned a while back is S is the arc length equals R theta. And where theta is the angle, S is the arc length, and R is the radius. All right, so we'll go ahead and label those radius and angle. And this is the formula that's used to figure out the circumference of a circle. The arc length from one point on a circle around it back to the beginning again, that arc length is the circumference. And you might recall that most people remember this one instead of the arc length formula, but that's 2 pi r. It's 2 pi radians times the radius. So that's our 2 pi is the angle times r. This is the circumference formula right there for a full distance around. So the realm we're taking this into in our study of rotational motion is, let's say I've got a rigid body, an object, let's say it's me and I'm holding my fist up here. If I rotate through an angle, then my hands traverse an arc length around the circle. You can kind of see that from your perspective there. So if these are my hands, this represents one of my hands, and then if I rotate my chair, one of my hands is being held at a radius r, and it'll traverse an arc length around a circle to some other point. Here we have rotational motion. That's the beginning of rotational motion. The beginning of translational motion is if we take one object that moves from one position to another, it translates from that one position to the other, and we get into distance and displacement, and then the rate of that change is the velocity, and the rate of that velocity change is the acceleration, and it just springboards into kinematics, the study of motion from there. This is where we're springboarding. But do you notice we're not moving a distance, we're rotating through an angle. There's a change in angle that happens here. So really, we're not looking at this just as a measurement of a circle, but the measurement of change. How far did my hand move when I rotated it? It's actually moving in the room, but it's moving about the center of my mass. So I'm a rotating rigid body. There is a change in angle. If I multiply that change in angle by the radius, I'm going to get a change in what we can call the position around the angle, around the outside of the circle. So my hands traverse an arc position, okay, a position around that circle, if we multiply radius times the change in angle. This looks a little more complicated than it needs to be, so if we just return it to S equals R theta, kind of like when we would do something like V equals X divided by T. There's really a delta X divided by a delta T. It's just a way to shorten it, a little easier to look at, and that's what I'm going to do here for this conversation we're having. All right, so now I can move my hands a couple different ways. I can rotate them slowly, or I can rotate them quickly. And of course, I can rotate more than that, just that angle. I can rotate all the way around, or 2 or 3 times around, or 5.5 times around. So that'll just be 2 pi radians times 5.5 will be the number of radians around. That would be a delta theta. Just an example of what we can do there. But if we have a change in theta, I'll bring it briefly back to the delta look here. Change in theta times r to get a change in our position around the circle. What if we divide both sides by a change in time? We get a rate of change. A delta S over delta T, this is a distance traveled divided by a time increment. So what is this? This is a velocity. It's a velocity. I'll come back to the direction aspect of that in a moment. And that would give us over here an R times a delta theta over delta T. We actually need to define something new here. If this represents a velocity of, let's say, my hands, how fast my hands are moving around the circle, then what would this rate of change in angular position be? What could we call that? I'm going to define a new quantity here called omega. It's a lowercase omega. This looks kind of like a W. Okay, we usually write W like that. Omega has more of a curl to it, oftentimes. Get rid of some of those. So I'm going to write this down. This is the Greek letter omega, and it stands for angular velocity. And I'm going to kind of showcase all these terms here to wrap this up after I introduce these. So I'm going to come back and go over these definitions and talk about what the words mean in just a little bit. But angular velocity, it's coming from a change in angle, an angular displacement. You'll get an angular velocity. So we get S equals R theta. And now we have V equals R omega. And I did say I was going to talk about the direction now. Now if these do represent my hand and I rotate counterclockwise here, then the velocity is in this direction when my hands are at this point. But when they're in this position, the velocity is directed this way. And you should note that the radius and the direction of the velocity are always perpendicular to one another. In fact, radius actually is a vector. Radius goes from the center of that circle to the outside. It's always going to the outside like that. The radius and the velocity are always perpendicular. That makes this velocity, to give it a direction, makes it a tangential velocity, because this is a tangent arrow, a tangent line. So the tangential velocity of a point on a rotating body is equal to r omega. Tangential velocity is r omega. And finally, what if, or as a last step here, last thing I can do, please note that if we speed up the velocity of that spin, it won't be just rotating at a constant rate, it'll be speeding up. For example, when you turn on an electric fan, the fan blades start to accelerate their spin and get faster and faster and faster. Then there's going to be a change in velocity, and that will cause a change in angular velocity. It'll start spinning faster, and that edge speed, this tangential velocity, will increase. Imagine if you're on, let's say, a carousel, and it's going around as it's starting up. You start to get a higher and higher speed. You note that you're going kind of forward, but you're also turning. So your perspective is changing. You're twisting around. As the carousel spins faster and faster and faster, your speed increases also. So this is your speed, and this is the increasing rate of angular velocity. If we measure that rate of change with respect to time, look what we have here. So if we divide both sides by delta t, delta v over delta t, of course, is an acceleration, and that's in the same direction as the v, so this will be a tangential acceleration. This point will speed up its tangential velocity, increases tangential velocity. Our r still remains a our r still remains a coefficient in there, and just like this became an angular velocity, we're going to have an angular acceleration. And this is the Greek letter alpha, lowercase alpha. And this represents an angular acceleration. There it is. So, 3 formulae there, 3 things that relate the translational motion of an object or a point on a rotating object. Let me say that again. 3 formulae that represent either an object that's on a rotating body or a point on a rotating body. What is that object's or that point's location? What is its velocity? What is its acceleration as compared to the angular displacement, how much it turns through, also compared to its angular velocity and angular acceleration. So those are our comparison pieces. These compare translational motion to rotational motion. So this would be important to keep in the back of our pocket as we're going through this unit. You always need to keep these fresh. They're always going to keep popping up exactly at the time you need them. Okay, so here are a couple of scenarios where you might need to use this particular one. We're going to go to the one in the middle, v equals r omega. Okay, remember this is a tangential velocity. I've got a couple of gears or cogs here that touch right there at that point. We'll call this one 2 meters in radius, and I'll give this one a 1 meter radius. There we go. So R1 is 2 meters, and radius 2 is 1 meter. All right. So these are actually two different scenarios. They're not the same thing. I'm going to come to this one in a moment. What's common about this one is they have a common edge where they come together. And for the second one, what they have in common here is a common axle. So they have a rotational axis that's in common. Okay, so if we have this kind of scenario, let's give this purple wheel, wheel number 1, an omega of, now I'm going to start introducing angular velocity here, 5 radians per second. We're not working in degrees or anything like that. It's only radians because radian is a real number. It's what we can multiply by a radius to get an arc length or arc distance, if you want to call it that, an angular displacement. So let's say this point, this object at the end here, or this point at the end is rotating, is moving as this disk rotates. And it'll move through 5 radians every second. So if you can imagine, a full cycle would be 6 pi radians per second. Pardon me, let's go back a little bit there. A full circle would be 2 pi radians per second, which is a little over 6 radians per second. So 5 radians, if you remember the radian circle, would be about 1, 2, 3 is a little less than half, 4, 5 would be somewhere about right there. That's the rate of rotation, 5 radians in 1 second. Just get a feel for that. It's good to think about those. So my question here is, if that is the angular velocity of disk number 1, what about this disk number 2? What would its angular velocity be? All right, it's not too hard. But what you do need to know is, what is the connection between these two? The connection is their edge. You see, the purple wheel, wheel number 1, its edge at that point is moving in this direction with a certain velocity. Guess what? That's where the wheel number 2 touches also. So as long as there's no slipping, what that means is if there's no slipping, then they're exactly clinched together. They're not sliding up or down. The edge of wheel number 1 is moving at the same exact speed as the edge of wheel number 2. So they both have the same exact velocity. I'll make a note of that. Same tangential velocity. So if we were to, let's say, write out v equals r omega for number 1, and v2 equals r2 omega 2 for wheel number 2, if they have the same edge velocity, that means that v1 is equal to v2, and r1 omega 1 is equal to r2 omega 2. Makes it very convenient for us. You see, all we have to do is plug in our known radii and the angular velocity for the first one, 5 radians per second. Plug in the radius of the second one, 1 meter, and it's very easy to solve for that angular velocity of the second one. So 2 times 5 is 10, divided by 1 is still 10. So omega 2 is 10 radians per second. Let's take a step back and think about that. Does that make sense? Every time the purple wheel, number 1, rotates around 1 time, so for every 1 revolution, a point on the edge travels twice as far as on wheel number 2. So if we rotate this one around once, number of radians per second, and the edges are stuck together, that means this one has to rotate around over the same distance, which would also have to be the circumference of this one. But being a smaller wheel, it's going to rotate more, exactly 2 times more often. So every 1 rotation of the purple wheel will give us 2 rotations of the green wheel. That's why its angular velocity is twice that of the first one. All right. So what's common here? Every time the purple edge goes around 1 time, for every instance of that. How many times does the green edge go around? Exactly 1 time. They have a common axis. They're spinning at the same angular velocity. Here we have the same omega, the same angular velocity. Okay? So if we compare V1 equals R1 omega 1 and V2 equals R2 omega 2, if they have the same angular velocity because their axles or the axes are connected, that means omega 1 is equal to omega 2. And if we solve that ratio, V1 over R1 would then equal to V2 over R2. If we start again, if omega has a angular velocity of 5 radians per second, that means omega 2 is also 5 radians per second. But what would its edge speed be? E2 might be something we're looking for. As long as we know the edge speed of the first one, oh, well, if you're given an edge speed, I guess this is where it's helpful. But in this case, we're given an omega, and I could just, substitute a R1 omega 1 up here, and we'll see that a little bit of cancellation. What this is really telling us is that if omega 2 is to V2 divided by R2, and omega 2 is equal to omega 1, see, that's all we got left here. Then, if omega 1 is 5, then omega 2 is 5, and we can come up with the edge speed of that second one. R2 is 1 meter again, so our edge speed is 5 meters per second. Now you might be saying, hold on, Mr. Schallenberger, where do the meters come from all of a sudden? Well, that's what I want to get into in the next screen. In translational motion, we have the quantity of displacement. And we use a delta x to determine displacement. Now there is a direction to that, so displacement is a vector value because it has direction. Likewise, angular displacement also has a vector value. It's got a direction to it. Angular displacement. And again, just like delta x, we have a change in position. This could be delta y or delta r, a lot of different things. There's only one symbol for angular displacement, unless you're dealing with different angles. The angle is theta, so angular displacement will be a delta theta. So when an object rotates from an initial angular position to a final angular position, we've got a delta theta. And instead of units of meters, we've got units of radians. Radians. I usually shorten it to rad or just r. Next, we've got velocity, or translational quantity velocity, and that's just a v, v for velocity. V is equal to delta x over delta t, so displacement over a time increment. In our rotation world, we've got angular velocity, and that symbol was already introduced as omega. Now, unit there is radians per second. We're just dividing the delta theta by time. So radians per second is a unit for angular velocity. How quickly does angle change? That angular position change. After that, we divide by time again, and we get acceleration and angular acceleration. Denoted by the Greek letter alpha. And this would be in radians per second squared. All right. Moving on, past this first section of our unit, we're going to be looking at the rotational analog of, an analog, by the way, if you hear that word, analog, think like analogy. So this is like. In the rotational world, this new quantity is like this other quantity in the translational world. So it's called the analog. So there are other rotational analogs of translational quantities. So others that we discuss in physics definitely are mass, which is m. Now mass has a gravitational aspect with translation, but in rotation, gravity doesn't cause an object to rotate unless it's acting unevenly on that object's center of mass. So it's mainly the inertial mass that we need to be concerned with in rotation. This m, like F equals ma, that m is a inertial mass, not a gravitational mass that affects acceleration. So in the rotational world, you can either call it rotational inertia or moment of inertia. The moment of inertia. We'll talk a lot about this later on. I, moment of inertia, capital I. And it'll have units of kilograms meters squared. Kilograms times meters squared. I also mentioned force, capital F. In the rotational world, a force that causes rotation to happen, or rotational acceleration, also called angular acceleration, that would be called torque. And that is a Greek letter tau. Looks kind of like a T with a hook, so Greek letter tau. And those units are Newton meters. A little while back in our energy unit, it says be careful, don't call joules Newton meters, because this is actually the unit for torque, Newton meters. And we'll see the difference there. This is not an energy, it has a direction to it, it's a vector quantity. And that's torque. So these are our main new ones. There is no rotational time, thankfully, so time is still time. Now we will get into other things like angular momentum and such, and I guess we can move a little bit into that. There is an angular momentum. So while we use P for translation, angular momentum corresponds to angular velocity. Very strange symbol though, it's symbol L, capital L. And this is similar to momentum, like kilograms meters per second, but we're going to be multiplying it by a radius, so a distance. So it's actually kilograms meters squared per second squared, or per second, sorry, kilograms meters squared per second. And that's angular momentum. So these are our main new quantities to introduce during the unit. There may be a few others just thrown in there. But the letters change a little bit. They have analogs. They relate to one another. They're very similar in action and how they're used. All these equations will look exactly the same in their form. Even though their letters may be different, the form is still the same. In the previous slide, I was talking, this is the last point I want to make, I was talking a lot about how we went from radians per second to meters per second. So I'm going to showcase our new introduced formula here for the tangential velocity of a point as it rotates around. Now when we take this unit-wise, velocity is in meters per second, so we should get a meter per second out of this. Now if you think about the units of radius, our standard unit is meters, and for angular velocity, radians per second. So why is this not written medians or meters radians per second? Okay, so in effect, what are we doing? We're ignoring this radians. Radians is a count, a number. It doesn't have a physical unit to it. So the difference between frequency and angular frequency or angular velocity is frequency is measured in inverse seconds, a number of rotations or repetitions or revolutions per second. Omega is 2 pi times frequency. In other words, instead of 1 revolution, we've got 1 revolution times a radian, times 2 pi radians per second. And that's just a hidden unit in there, is that radians. So we got, for omega, we got radians per second, because we're multiplying frequency by 2 pi. It's still a count, it's still a number. This little 1 here has revolutions or repetitions or cycles in it. It's still a count of something, but it's not a physical dimensional unit. So all we're doing here when we write radians per second is signifying this is an angular radius. It's not degrees, it's not revolutions, it's a radians per second. It's just the count. So when we do get a physical quantity multiplied in there, a dimensional quantity, meters, takes up space, we're just going to drop that radians out of the picture and write meters per second. And so the final thing I've done here is I have talked about some quantities of rotation. So just to finish those up, there is a relationship between 3 quantities that involve time, and that is frequency. Frequency is the inverse of period. Got frequency over here, got period over here. So if a certain spin takes about 2 seconds for an object to rotate around, its frequency is 1/2 rotation per second. And then finally, just to bring this full circle, the relationship between omega and frequency is 2 pi f. So that'll give us number of radians per second. And of course, that can be written 2 pi over period, if we want to relate period to omega. And that's it. That'll get us started in rotation, and we'll be able to springboard here into rotational kinematics and all that good stuff, spinning, speeding up, slowing down, and such. So I hope this presentation will be helpful.